All right, thank you, everyone. We have Devon McKee is going to give a talk about GPU performance modeling with Microbenchmarks. Take it away.
So hello, everyone. My name is Devon McKee. I'm a second-year CSE PhD student at UC Santa Cruz. I currently work with Tyler Sorensen, who is here at the Concurrency and Heterogeneous Programming Lab. And I work with kind of GPU synchronization. This is to say on-device synchronization, not CPU-GPU synchronization, performance modeling, and kind of dynamic work allocation on GPUs. So I'll start this presentation just a little bit with, there's my arrow keys, CPU atomics. So all of you have worked, I'm assuming all of you have touched CPU atomics at some point in your life, but we'll go through a little quick kind of diagram simplifying some of CPU atomics. So you have a thread, in this case I've called it thread 0. We're using atomic RMWs, which is what this talk will primarily focus on. It's performing an atomic fetch add type of read modify write RMW. It'll attempt an operation on some memory location A, and it'll try and lock that cache line. Then another thread comes in, tries to do the same operation, and it will have to wait because thread 0 is currently operating on that location. Thread 0 eventually will finish its operation. It'll release its lock on this cache line, and thread 1 will come in and perform its operation. So because of this exchange, CPU atomics have a pretty well-defined performance profile. Threads that need access prefer to lock cache lines when they can. So this is kind of a simple benchmark that I put together where on my AMD Ryzen CPU at home, I get about 73 atomic operations per microsecond. This is with atomic fetch adds, with this diagram here kind of describing what's happening. We get as many threads as we can on the CPU, 16 in my case, and we give them each their own location to perform an atomic fetch add-on, and we try and do that as many times as possible and then test the throughput over that period of time. So we notice that threads that need access prefer to lock those cache lines. What this also means is if you have threads contending on the same location, then their throughput is hurt. So this second diagram here is kind of illustrating the situation in which you have threads contending on the same location. I've kind of color coordinated here. So all of the red threads here you see are performing the access on the first location, all of the blue threads performing access on the second location, etc. And with this test, I get a throughput reduction. You'll notice before it was 72 atomics per microsecond, and now it's 40 atomic operations per microsecond. In the inverse here, because they like to lock cache lines, if we pad our atomics out to cache line size, we get better throughput. You'll notice here that my atomic throughput is much higher. We've got 387 atomic operations per microsecond on the same CPU. And this kind of is not a perfect diagram because it's not padded out to cache line, it's actually just padded twice. But our tests kind of look like this. You have a bunch of threads. There's, I guess, only 8 in this image, but those threads are distributed across an array of atomic integers, and we pad them out to some size. In this case, because it's an AMD CPU, cache line 64, 4-byte integers, we've got 64 bytes. You have to pad them out 16 times to get each cache line to be operated on by a different thread. These results altogether, I feel pretty comfortable about, and I feel comfortable enough to say that there's a live demo here that you should be able to run on any laptop, mobile phone, anything I've tested it on has worked so far. Any browser that you have that runs shared array buffers, so Chrome, Firefox, any of the others that support shared array buffers will work. In fact, it works on my iPhone, which is interesting. That test will run all 3 of these things you just saw here, and it'll also create a heat map. So we look at a lot of these heat maps. So I realize that I have to explain a heat map every time that I show it. In this case, the first parameter that I talked about, threads contending on the same location, we call this contention. Contention is what we sweep on the x-axis of this heat map. So you'll see as we increase contention, there's more threads attacking the same location. On my CPU at home at contention 16, that means all 16 threads are operating on the same atomic location. In the inverse here, on the y-axis, we have padding. So padding, as we measure it, is basically just how many atomic integers do you have between the ones that you actually use. You'll notice that the results that we see here, we kind of expect. As contention increases on the bottom row here, we'll just kind of go through this simply. There's contention 1, padding 1, the baseline here, 40 atomic operations, 41, I guess, per microsecond. This corresponds to the first diagram. Another point in this graph, 4 threads contending on the same location with no padding, corresponds to the second diagram you saw. The third, kind of just specifically this area, because this diagram is only padded out to 2, corresponds with this location in the heat map. You'll see as you sweep upwards, At 16, you hit cache line size and your throughput goes way up. I'm, again, pretty confident that any CPU in this room, and if you have ones that don't look like this, please tell me, will look like this heat map. I'll talk a little bit about GPU synchronization before I move on to that, though. So again, talking about GPU on-device synchronization, so atomics specifically. But anyway, GPU compute is becoming increasingly critical. So a lot of you are doing a lot of compute, not just in your kind of general purpose compute workloads, but a lot of people are doing a lot of compute and even rendering workloads here, because the graphics pipeline is not always as malleable as we want it to be for some of these tasks. GPUs generally are highly concurrent processors. They give you a lot of concurrency, and with that means that you have to run heavily concurrent algorithms that require synchronization between workgroups. This means that you have to have some kind of synchronization that happens while your GPU is still in flight. GPU synchronization specifically comes in the form of two major primitives that we examine. Atomic instructions, in this case we focus on atomic read modify writes. We have some other work that should explore many of these other variants here. But also barriers, which is something we also have work on that we're starting to work through. But specifically, we're going to talk about atomic read modify writes. So GPU atomic performance varies greatly across these devices. They're sensitive to a ton of different performance characteristics. Two of them you've already seen, contention and padding, threads containing in the same location, and locations padded out to maybe some size. The other thing that they're sensitive to is the access patterns. So GPUs are not, I used this term in my last run of this, GPUs are not flat. CPUs are not necessarily flat either, but the performance models that GPUs have are very hierarchical. You've got subgroup, warp, wavefront, whatever you want to call them. You've got these groups of processors running in tandem that execute at completely different times. And that hierarchical nature means that the access patterns distributed across these workgroups or these subgroups is completely different. So I'll talk a little bit about the thread access patterns that we examined in this work here. The first one we just call contiguous access. It means that we take all of the threads we can on our GPU, we run a little occupancy discovery protocol, we try to run it full occupancy, get as many threads in flight as we can, and then we just distribute those threads chunked across warps, within warps. So we take, for example, if you have 8 threads, as in this diagram, you start with warp 0, just take threads 0 through 7. And we'll chunk those out. In our second test, we do cross warp. So we try and stride our accesses across the warps in the system. This is a little bit of a contrived example because you've got 2 warps in your system, and I hope none of you have GPUs that have 2 warps that can be in flight. But we kind of stride those across this array of atomic integers that we create. The third access pattern that we have here is random access. So we take every single thread we can get in flight on the GPU, and we distribute it randomly across this array of atomic integers. And in this test, we specifically vary the size of the array, meaning that if your size is 1, every single thread on the GPU is trying to access this one spot. If your size is 16, there's 16 locations that randomly get distributed. We do some work to preempt the question to make sure that it is actually random. We do randomness in CPU and then pass indices for each test independently to make sure we're distributing these things randomly, because GPU randomization is a complex topic. So we have a series of microbenchmarks here written in Vulkan that currently target atomic read modify write instructions. They're pretty simple microbenchmarks. These are 3 of them. They're a few lines of code. You'll notice they're written in OpenCL. The whole test is written in Vulkan because we want cross-platform testing. We don't care about this on just Nvidia devices, or we write CUDA. We don't care about this on just Apple devices, or we write Metal. We care about this on every single platform we can get, which is why we use Vulkan. It is a C++ application that we are currently trying to rewrite to work on some of our Android devices, and I'll talk a little bit more about that in future directions. And we use OpenCL kernels that we transpile to SPIR-V using CLSPV, which is a Google-provided tool that is a transpiler from OpenCL to SPIR-V, and we then execute that SPIR-V in our Vulkan application. We produce benchmarks that sweep values for contention and padding, like the CPU benchmark that I mentioned before. We have separate benchmarks for each access pattern that I also mentioned before. And eventually, we produce heat maps that show these trends in throughput. Again, like the CPU heat map you just saw. But we've seen what these look like on CPUs. And again, if you have a device in this room that does not run this heat map, does not look this way, really curious to see what it is. Because on GPUs, they look really, really different. These are 4 different cards, 4 different vendors. I think 2 of these are different tests, but the distribution pattern looks very, very different. So what do we do with this? Let's just do a little case study here. This is an Intel discrete card. It's an ARC A770. This is with our contiguous access test. We notice that there is peak throughput here. And so again, for those of you that have not seen many heat maps or have not looked at this one long enough to realize what's happening, at the start, at the top here, the yellow is the highest amount of throughput. It's at around 16,500. And you'll notice that contention 1, padding 1, meaning that every thread is gets its own location and we're not padding them out at all. For some reason, that gives us great throughput. If you look at the as on the upper ends of this graph, as padding goes down, you notice we lose, from 16,500 down to about 2,000 operations per second. So that's a pretty significant decrease as you increase this padding. And similarly, as you increase contention here, if you contend about 64 threads in the same location, you get all the way down to my tiny little text here, 800 atomic operations per microsecond, which is a significant decrease. And again, looks nothing like we expect in the CPUs. The throughput in this case degrades down to less than 5% of the peak throughput in some of these scenarios. Another case study, AMD discrete card results. This is an AMD RX 7900 XT, which is an RDNA 3 device. It's Navi 31, I think. It gives us peak throughput at contention 4 and padding 1, which is an interesting number because what do you do with this? You've got 4 threads accessing the same location, and there's no padding between them, and this gives us throughput of a little around 33,000. But if you notice some of the other points in this graph, take some of the extremes out here. We pad these atomic operations out. We say 1 thread per location, and we pad that out to maybe we only use 1 every 32. This goes down to about 200 atomic operations per microsecond. That's a significant difference. I don't think I need to tell you that's a significant difference, but it degrades to all the way down to about 1% of the peak here. Another case study, Nvidia. This is an Nvidia GeForce RTX 4070. This is an interesting graph. We've spent a lot of time talking about this graph. You get peak throughput past contention 32. You will also remember, if you've worked with NVIDIA GPUs, that NVIDIA warp size is 32. This means that anytime 32 or more threads are contending on the same location, and quick note, we do increase these at log size. You'll do 32, 64, 128. May not look the same if we were doing 48. Kind of a strange number to distribute these across, but for our purposes here, you'll notice that just past contention 32, we get this huge jump in throughput. It's about 2,800 atomic operations per microsecond. And then anything less than that, save this little trend on the bottom here, about 112 atomic operations per microsecond. So what do you do with this information? GPU atomics are starting to get really, really complex. The slower region is about 4% of our peak throughput. So another case study. This is the crosswalk test that I mentioned. I'm not going to speak too much about this one, but just know that we have probably another 40 or 50 of these heat maps I could spend the next 3 hours going through with you. And we have spent much of this time going through these heat maps. Our crosswalk test, this is for the same card that you saw for AMD before, the RX 7900 XT. It gets peak throughput at contention 32, and then kind of just degrades outwards as you sweep away from these parameters. So there's a sweet spot somewhere here, and it really depends on what your access pattern looks like. The random access microbenchmark, one that I mentioned earlier, where we try and take as many threads as possible and we distribute them across this array of atomic locations. I just said that. We vary the size of the array to distribute the threads more. So if I take this array and it's 1, every single thread is going to try and attack this one location. If I increase the size of the array to 16, every single thread is going to try and attack one of these 16 locations, etc. Here's our results for the AMD card. You'll see that kind of at 1, there's 1 atomic location for them all to access. Throughput's pretty bad. It increases all the way to 16, and then there's a local maxima, and then it increases past 64, presumably ad infinitum. I mean, we haven't spit that far. But what this tells us is that if you have a lower number of atomics that you need on these GPUs, maybe you should just bitpack your atomics. If you have a thread access pattern that's sufficiently complex enough to be represented by randomness, then maybe you just want to bitpack your atomics together until you have only 16 that they're accessing. Or maybe you have way more than that, and you want to just spread them out as much as possible because your throughput's going to get better. Same case study. NVIDIA RTX 4070. the throughput falls immediately as soon as your number of atomics increases. At atomic 1, like this matches up with the heat map you saw before, because at 1, you get maximum contention. Every single thread is trying to attack the same location here. And NVIDIA loves that. But if you can reduce your number of atomic locations to 1, you'll get great throughput. Panels do that. But how do we characterize these results? So we, again, have 40 to 50 heat maps to work through, and they're not always so easy to talk about. I put this one up on the screen because we talk a lot about this one. It's really fun to talk about. No one expects a heat map to be bimodal. Can we, and not just how do we characterize results, but specifically, can we create atomic performance profiles that we can reduce to conditions that give greater throughput on different devices based on these profiles that we've gotten from our microbenchmarks? So working on creating an atomic performance model that will allow us to describe their behavior as we sweep through these characteristics. The basic model as we've worked through it right now involves some kind of access pattern. There are parameters of that pattern that are informed by your application, and then there are some conditions that are informed by our results. And basically, it's a simple little flow chart right now. Simple model that tells you, you have some parameters, you have some device that has some characteristics. Can you get peak throughput, or are you going to get below peak throughput? Obviously, there's a lot of complexities to this. These complexities make it really hard to identify conditions. So I'll go through one example you've seen before. This performance model is for the Nvidia GPU we saw before. So take a single point in this chart. You have a contiguous distribution of threads with chunks of 64 threads attacking the same atomic location. Technically, that's not one point in this chart. That's because I didn't specify padding. That's a line here, a column. But because at least 32 of those threads are contained in the same location, we say we're probably going to get peak throughput on this NVIDIA device. It's a little harder for some of these other results. This is the AMD cross-warp test that I mentioned earlier. We distribute these threads across warps, strided, and there are some conditions, and those give us some function of peak throughput. So a lot of the work here is trying to reduce this into a model that makes sense. And this is where the work is kind of evolving every day. If you talk to me next week, we'll have a very different understanding of how this works. But right now, we have a lot of data and a lot of thought to do about it. And we're trying to create a model that people can work with. So a summary of some of the contributions here. We've done a study of relative atomic performance across GPUs. You'll notice I have not specifically said, well, this GPU is better than this GPU, because it's not a fair comparison. Microbenchmark suite that we put together in Vulkan to be executed on any device supporting Vulkan, which, as many of you know, is a lot of devices. Also, we're trying to work on a general performance model that allows us to capture the complexities of GPU atomic performance. But how do these results help us optimize applications? It's a very important question here. Again, these graphs are confusing to look at, even if you've been staring at them as long as I have. The hope is that a sufficiently appropriate performance model allows us to structure our atomic RMWs as device-specific atomic optimizations. If you can have some conditions that you know are going to give you better throughput for your atomics, and your application cares about the performance of GPU atomics, you want to know that you're not going to land in the blue region of these graphs. You want to know that you're going to land in the yellow region of these graphs. You want to have some understanding of how you have your access pattern in your application, which, again, like I mentioned earlier, some of the access patterns are complex enough that they can be represented best by randomness. Some of them are not. And the hope is that we can look for opportunities to include these as some kind of device-specific information in Vulkan. This is maybe the call to action here, is that as Vulkan developers, as people involved in Vulkan, we love Vulkan. It's a cross-platform API that allows us to run our tests everywhere. But the hope is that these results don't just sit at the state of, well, I have a really important application. I'm going to run some crazy tests, and then I'm going to do this. We hope that this kind of extends a little bit more into how can we enhance the Vulkan specification with these results. So some future directions. We've looked at kind of setting an atomic or a GPU simulator as a baseline, and then modifying the atomic implementation to kind of recreate some of what we think is happening on these cards, and see if we can examine those effect in applications. So if you have applications that are GPU atomic bound or care about the GPU atomic performance, and again, this is another call to action. If any of you have applications that depend on GPU atomic performance, please let us know. This is a very important part to us. Also hoping to expand our testing to new devices, including mobile platforms at Apple devices, and especially Apple devices through Molten VK. I've gotten at least one of them running on my M3 MacBook. very nice. But we're trying to run on a lot of these mobile devices too, like the ARM Imagination Qualcomm GPUs, anything we can run on. Finally, we're hoping to apply this methodology that we used for this talk to other synchronization primitives. I mentioned barriers at the start. Atomic RMW specifically are not the beginning and end of GPU synchronization on device. So I think that is the end of my slide. Thank you all for listening. Yeah.
I see we have hands raised. Do we have questions?
So your NVIDIA numbers are very puzzling. I have one concern about the approach of using Vulkan and to do this best portably is that maybe you're falling off like some of the layering would cause you to fall off the the fast path, and you end up with some from emulation. You're not actually benchmarking whatever the hardware can do. Is that something you have accounted for? You have something to say about?
Yeah, I mean, certainly the last thing to say about as we explore that more. It's like a serious concern. I mean, having seen a lot of these talks in the last couple of days, there's a lot of layers that Vulkan goes through to run code on the devices it does. But at this point, we have been operating mentally from the perspective of a developer using Vulkan, rather than try and speak about, well, this device is definitely doing this, or this device is definitely doing this. We're trying to get to a point where our tests are coming from, I'm trying to write an application on Vulkan. Am I going to expect to see these access patterns? But you're right, there's some more work to be done on confirming that our tests are not being mangled by some step down the line.
So if I'm understanding correctly, I think I can explain you NVIDIA graph pretty easily. One thing that a lot of compilers do is an optimization where they detect if the entire warp is going to hit the same memory address. They will just do a single atomic for the whole warp, and then make it look like it happened on every single thread. And that's probably what's happening. And it's pretty standard, especially if you have, and you'll also see that the more common case is if you have like a single atomic counter that's being used by everybody, it's easy to do that. But if they can also back out the index offset calculation that you're doing and figure out that per warp it's uniform across the warp, then they'll just do that. So that's probably what it's doing. So it's not actually really a hardware thing necessarily. It's just you're hitting a compiler optimization. There is some hardware that also optimizes that under the hood potentially. And some hardware doesn't have per invocation atomics, and they actually have to loop over the warp. So there's a bunch of different things that could be going on, but most likely I think some of what you're seeing, particularly below 32, is probably more about compiler optimizations than it is about actual hardware behavior.
Yeah, it's very likely. I mean, we have a lot of steps between that, and not even just at the software side. There's a lot of steps on the hardware side. The cache hierarchy of those NVIDIA cards, completely different than the AMD cards, completely different than the Intel cards, and certainly different than the mobiles. Yeah, so I mean, it's an effect that we're examining. We're also trying to kind of split the work between analyzing this very precisely, trying to like tack down exactly what's happening, and also analyze this from the perspective of, well, we can only see so much as Vulkan developers. Like, we only have access to so much of the system, and maybe it means that from that perspective, you can't say as many things about the card, but you can also say things about what your Vulkan implementation on your driver, on your device is running. So it's a little bit of both. And this is kind of where the work is evolving over time.
All right. Do we have another question, or shall we move on? Okay, one more question.
Yes, I was wondering if you had investigating trying atomics and data that went much further than for instance, the capacity of the L3 cache, because I remember having very confusing results with atomics on images that were above the L3 cache, and I think it would be interesting to see what different GPU vendors perform in this space.
So if I understand your question correctly, it's that there are some interesting results past the size of,
because
of the L3 cache.
I get once I get past about the L3 cache size, I tend to get, well, of course, a lot of VRM throughput and exclusively when my atomics are completely incoherent. If they are somewhat coherent, it tends to cache a lot more. Maybe it's not just relating to atomics, but yeah, I've had kind of confusing results with that.
Yeah, I mean, I will tell you that in our meeting last week for this project, we had essentially this conversation of like, we need to sweep out past certain parameters of like, you know, we're examining the effects of multiple cache hierarchies. And again, through compilers too, we have to kind of sweep these things as far as we can get them. So I think that'll be an interesting venue.
Okay, thank you.
All right, one more round of applause for Devon.